under the unit current electricity, first let's learn what current is. So now, what is current? In order to learn this, consider a conductor with a cross-sectional area A. This is a conductor. So current is defined as the amount of charges flowing through a certain cross-sectional area in a unit time. So for 1 second, the amount of charges flowing through this cross-sectional area is defined as current. So the sign we use to denote current is I. So we can write it as I equals Q divided by T. Q means the amount of charges, T means time. So the units of current will be, units of charge is coulomb, units of time is second. So the units of current will be coulombs per second. Now this is equals to amperes. Ampere is the standard unit of current. So the equation for current can be written as I equals Q over T. So here Q can be written as IT. Q is the amount of charge. Also Q can be written as NE. What is N here? N is the number of charges flowing per unit volume. What is E here? E here is the charge of an electron. Now why we consider electron? Because in our lesson is current electricity. Current is the flow of charges. So in current electricity, we learn about the flow of electrons. The charge here is electron. So we can write Q as NE, number of charges flowing per unit volume, into the charge of an electron. Okay. Thereby, IT can be written as equal to NE. So I equals NE over T. This is also a derived equation. You can remember this easily for questions. So this is basically the equation you should know for current. Now let's talk about the mechanism of current flow between the terminals of a conductor. Here let's consider a metallic conductor like this. In metallic conductors, ionic lattice is formed by the removal of freely bounded electrons from the outermost shell of atoms. So it forms cations and electrons which are mobile. These electrons move randomly in different directions at very high speeds. But here there won't be a current flow. Why? Because if we consider a particular cross-sectional area of the conductor, the resultant amount of the electrons which flow in one direction across the area will be 0. So the current will be 0. Here the net current will be 0 in this case. So in order for current to flow in a conductor, we need an external electromotive force, means a battery, connected to it. So when an external electromotive force or a battery is connected to the two terminals of a metallic conductor, a potential difference is created across the two terminals of it. This potential difference creates an electric field. So this electric field creates forces on these mobile electrons. So these electrons which were moving randomly earlier now starts to accelerate to against the field, means towards the negative terminal of the battery. These electrons start to accelerate like this. So there will be a net flow of electrons to one direction. So this creates an electric current. So this is how an electric current is created in a conductor. So just a mere conductor, mere metallic conductor we say, won't have a current. It has to be connected to a potential difference in order for a current to flow. Here the direction of electron flow is against the field from negative to positive. But the direction of conventional current is from positive to negative towards the direction of the field. This is the direction of conventional current. So always the direction of conventional current is opposite to the direction of electron flow. When electrons move from the negative terminal to the positive terminal, means against the field, the electron flow is not smooth here because the electrons collide with the positively charged lattice ions and the velocity of electrons change time to time. So actually we call the electrons drift against the field. So the average velocity of an electron which drifts is called the drift velocity. And remember, the velocities of this each and every electron is different from each other. So the mean value of the velocity of electrons gives the mean drift velocity. So we denote drift velocity as V. This is drift velocity. The mean drift velocity means the mean value of the drift velocities of electrons is Vd. So now you got to know what drift velocity is. Now let's write an equation for the drift velocity. So drift velocity is the average velocity of an electron which moves from this negative terminal to the positive terminal. If we consider the length of this conductor as simple L and the time taken for an electron at the negative terminal to move to the positive terminal as T, drift velocity can be written as V equals L over T. Now let's consider the relationship between drift velocity and electric current. So we have found an equation for drift velocity as V equals L over T. So you know current I equals Q over T. So Q can be written as IT. Now I'll teach an important equation for Q here. Now Q is the amount of charge. Q can also be written as V N E. Now what is V here? What is N here? What is E here? V is the volume. N is the number of electrons per unit volume. per unit volume, and E is the charge of an electron. So now it's clear to you, when the number of electrons per unit volume is multiplied by the volume, you get number of electrons, and when it is multiplied by the charge of an electron, you get the total charge Q. Okay, so these two is equal. We can equal those two equations. So IT is equals to VNE. So this V is volume here. If we consider the cross-sectional area of this conductor is capital A, this V means the volume can be written as AL, and cross-sectional area into length. So IT equals AL NE. So then I equals AL NE over T. So now you see we have a term L over T here. So I can be written as AVNE. For the sake of memorizing this equation, I'll just tell you a simple method. We can write I equals NAVE. It's still the same terms, just the places where they are interchanged. In Sinhala we pronounce this as NAVE. I equals NAVE. So if in case you want to have a short way of remembering this, you can remember as I equals NAVE. I just told you. So yeah, that's about drift velocity. Now let's talk about current density. So current density is denoted by capital J. Now what is current density? It is the current flowing per unit cross-sectional area. So J equals I over A, current flowing per unit cross-sectional area. So the units of current density is, units of I is A, amperes, units of area is square meter. This is the units. Okay, so this can be written as ampere per square meter. This is the unit of current density. Now just in case you might confuse with density, usually density is mass over volume. It's something related to volume, but here this current density is not related to volume. It's related with area, cross-sectional area. So current density is current divided by cross-sectional area. So we need current density for instances like this. When the cross-sectional areas of a conductor is not uniform. When the cross-sectional area is not uniform throughout the conductor, we need this term. So if the cross-sectional area here is A2 and here is A1, always the current which flows through this conductor is the same. I is the current which flows. So here we can write J equals I over A. Since the current is the same for both the cross sections, we can write I equals JA. So for this, if we consider the current density as J1 and J2 here, we can write J1A1 equals J2A2. So we can build up a relationship like this when doing sums related to conductors with non-uniform cross sections. So you have to remember this equation, and also remember here, unless the conductor branches, the current doesn't change. You can say like this. No, this conductor can branch. So the current which comes like this, so when it branches, the current gets divided. Okay. Now let's define potential difference. What is potential difference? Between the terminals of a conductor. If we consider a conductor like this, potential difference between the terminals of this conductor is the work done by the electric forces that is used to move a +1 Coulomb charge, means a unit charge, from one end of the conductor. We consider this as plus n and this as minus n. From one end of the conductor to the other end is defined as the potential difference between these 2 points. So this is the potential difference. It's a work done by the electric forces that is used to move a unit charge from one end of a conductor to the other end. So the units of potential difference is joules per coulomb. This is a work done, so it's measured in joules. Work done on +1 Coulomb charge, so it's joules per coulomb, or you call it volt. So volt is the unit we use. So that's about potential difference. Now let's learn what is resistance. Now resistance is the obstruction created to the flow of electrons due to the collision of electrons with metal atoms and cations. So consider a metallic conductor like this with a potential difference applied across its terminals. So I taught you earlier, when a potential difference is applied, a field is created. So this electric field creates forces on these free electrons. So these free electrons starts to accelerate and drift against the field towards this positive terminal of the battery. So when these electrons starts to move, these electrons collide on these positively charged cations and atoms. In these conductors, metallic conductors, there are some atoms whose outermost electron is not removed as well. So these electrons collide on these cations and atoms. So this creates an obstruction for this flow of electrons. So that obstruction is called this resistance. So we denote resistance by capital R. So there are various factors affecting resistance of a conductor. Now, what are those factors? Now let's see. One of the most important factor affecting the resistance of a conductor is the temperature. So main factor is temperature. Now consider this a conductor, a metallic conductor at T1 equals 27 degrees Celsius room temperature, and at a temperature greater than that, in like 60 degrees Celsius. When the temperature is high, these free electrons have a greater energy, so they collide vigorously with these cations and atoms. Since they have a greater energy, they move faster, so the obstruction for them is increased at higher temperatures, not like in at room temperature or a lower temperature than that. So when the temperature increases, the resistance of a conductor increases. Okay, it's directly proportional. Also, the other factor, the length of a conductor. When the length is high, the resistance is high. That is, the resistance is directly proportional to the length of a conductor. So, like this. Here the length is greater, let's say. This is a shorter conductor. So, this resistance is high. Let's say R1, R2. So, R1 resistance is greater than R2 because its length is greater. Also remember, now when we consider the length, the other factors affecting the resistance of the conductor must be constant. Always we consider only one factor. So the next factor affecting the resistance of a conductor is the cross-sectional area. When the cross-sectional area increases, the resistance decreases. So resistance is inversely proportional to the cross-sectional area, like this. Consider a greater cross-sectional area like this and a smaller cross-sectional area like this. The same length here at same temperature. So A1, A2. Here the resistance of A1 or A1, let's say, is less than the resistance of A2 or A2. So thereby we can write R is proportional to the length, it's directly proportional to the length, and R is inversely proportional to the cross-sectional area. So at a constant temperature, we can write an equation. R is proportional to L over A. So here we use the proportionality constant rho here. What is this rho? It is resistivity. Resistivity of a conductor. This resistivity depends on the material of the conductor and it varies with temperature. So this is the equation you should know for the resistance of a conductor. R equals rho L divided by A. And now what are the units of resistance? Units of resistance is ohm. This is a standard unit, ohm. You should know this. So this is about resistance. Now let's talk about the definition of resistivity. So resistivity can be defined as the resistance of a conductor which has a length of 1 meter and a cross-sectional area of 1 square meter at a given temperature. So resistivity depends on the material of a conductor and it depends on the temperature. And the temperature. There's another term you should know, which is electrical conductivity. Conductivity. It is denoted by sigma. So electrical conductivity is the reciprocal of electrical resistivity. Sigma equals 1 over rho. Reciprocal of resistivity. And here the units of resistivity is ohm meter. And here the units of electrical conductivity is units of sigma is per ohm per meter. Inverse of the units of resistivity. So per ohm is actually called Siemens. Siemens per meter. Siemens per meter. And next we'll talk about electrical conductance. Conductance. It is denoted by capital G. Electrical conductance is the reciprocal of the electrical resistance. And the units of conductance is per ohm, inverse of resistance. Per ohm equals to Siemens. So now let's discuss about Ohm's law. What Ohm's law says is the current flowing through a conductor is directly proportional to the potential difference across the terminals of the conductor when the temperature and other physical factors are kept constant. Okay, so what it says is the current is directly proportional to the potential across the terminals of the conductor. So the proportionality constant we get here is 1 over R, resistance. Here it says temperature and other physical factors are constant. So that means the resistance is constant here. So we can write an equation V equals IR. So this is the equation you're gonna derive from Ohm's law. You should remember this equation. Okay, and now let's draw the graph between potential difference and current. It will be a straight line graph. V in volts, I in amperes. So here you will get a straight line which passes through the origin. So the gradient of the graph equals V over I and it is equal to R. Okay. Now let's talk about two types of conductors. There are ohmic conductors and non-ohmic conductors. So what is an ohmic conductor? When the VI characteristic curve drawn for this conductor is a straight line passing through the origin, we call it an ohmic conductor. So when you draw the VI characteristic curve for an ohmic conductor, it will be a straight line passing through the origin, like this. Straight line passing through the origin. So examples for ohmic conductors are gold, silver, copper and copper sulfate solution. These are the examples. And now when you consider non-ohmic conductors, we have three examples. First example is the tungsten filament of a bulb. Tungsten filament of a bulb. For this, the VI characteristic curve would be something like this. It is not a straight line passing through the origin. Okay. This is for a tungsten filament of a bulb. So the second example is thermistor. So the VI characteristic curve for a thermistor would be something like this. It's not like this. And the third example is semiconductor diodes. The VI characteristic curve for semiconductor diodes like this. For a semiconductor diode. You should remember these three examples for non-ohmic conductors. The graph VI characteristic curve for tungsten filament, thermistor and semiconductor diodes. There are questions from these.
මෙම වීඩියෝව ඔබගේ දැනුමට උපකාරී වුණා නම් ලයික් කරන්න. මේ වගේ තවත් වීඩියෝස් බලන්න අපිව සබ්ස්ක්‍රයිබ් කරලා බෙල් අයිකන් එක ක්ලික් කරන්න. ඔයාලගේ යාළුවන්ටත් දැනගන්න ෂෙයා කරන්න අමතක කරන්න එපා.